All right, let's talk about one of the most incredible elements out there, carbon. It's literally the foundation of life, and it's in so many things we use. But what's really wild is how this one single element can show up in such completely, and I mean completely, different forms. Welcome to the element of extremes.
So, on the one hand, you've got diamond. We all know it. It's the hardest natural thing on the planet, strong enough to cut right through steel. And then, on the other hand, you have graphite. You know, the soft, slippery stuff in your pencil. It's one of the softest materials around. I mean, we're talking about total opposites here.
But get this, both of them are made of pure carbon. That's it, nothing else. So how in the world does the exact same element create something incredibly hard and something incredibly soft? That's the big question we're going to unpack right now.
Well, the answer comes down to a really cool concept called allotropes. Allotropes are just different ways the atoms of a single element can be arranged. It's kind of like Legos, you know? You can take the exact same pile of bricks and build a super strong castle or a totally different spaceship. It's not about the bricks themselves, it's all about how you snap them together.
Okay, let's dive in. First up, our first case study, the amazing, unyielding structure of a diamond.
So what you're looking at here is the atomic structure of a diamond, and what's absolutely key is just how perfect and orderly this whole thing is. Every single one of those little spheres is a carbon atom, and you can see they're all locked into this flawless three-dimensional grid.
Let's break it down. So, picture this. It all starts with just one carbon atom. That atom then reaches out and forms four super strong bonds with four of its neighbors. Then, each of those neighbors does the exact same thing, and on it goes, building this incredibly strong, interlocked network in every direction.
And the result of all that? This ridiculously strong, tight-knit structure is what makes diamonds so legendary. There are simply no weak spots. Every single atom is held tightly in its place, which is exactly why we put them on the tips of drill bits and cutting tools. They are literally built to be unbreakable.
Okay, so we've seen the fortress. Now let's flip the script completely. How does the same atom turn around and create something as soft and slippery as graphite? Just take a look at this. The arrangement could not be more different. Instead of that 3D grid, the carbon atoms in graphite line up in these flat hexagonal sheets. It almost looks like atomic-level chicken wire, right?
And this is where it all clicks, the link between how it's built and what it does. See, in graphite, each carbon atom only bonds to 3 others, not 4. This is what creates those strong, flat sheets. But here's the kicker. Those sheets are just stacked on top of each other, and the connections between the layers are super weak. This lets them slide right past each other, which is why graphite feels so smooth and why it leaves a mark when you write with it.
But wait, there's another super important detail. To make those 3 connections work, one of them has to be a special kind called a double bond. And because of how that's set up, it leaves one electron from each atom totally free, just wandering around the sheet.
And what happens when you have a bunch of electrons that are free to move around? You get an electrical current. This little sea of free electrons is exactly why graphite conducts electricity, which is something diamond, with all its electrons locked up tight, just can't do.
Now, just when you think you've seen what carbon can do, it throws us another curveball. Or, in this case, a soccer ball. Let's look at a much more exotic form, the fullerenes.
Check this out. This molecule is called C60, also known as Buckminster fullerene. What a name. It was the very first one discovered, and as you can see, the 60 carbon atoms are arranged in a perfect sphere. It's a pattern of hexagons and pentagons, just like an old-school soccer ball.
And it gets that wild name from an architect, Buckminster Fuller, who was famous for designing these huge buildings called geodesic domes that look just like this molecule. But this is more than just a cool shape. These tiny carbon cages are opening up a whole new world in nanotechnology. Scientists are looking at them for everything from delivering medicine on a microscopic level to creating new kinds of superconductors.
Okay, so let's tie this all together and finally solve our original mystery. What is the real fundamental difference between something hard, like diamond, and something soft, like graphite?
It really just boils down to a simple number. In a diamond, every carbon atom makes 4 bonds. That creates the rigid, super hard 3D structure. In graphite, every carbon atom makes just 3 bonds. That results in those flat, slippery layers that make it soft.
And that right there is the big takeaway. A material's properties don't just come from what it's made of. They come from how it's put together.
When it comes to carbon, arrangement is absolutely everything.
This quote just sums it up perfectly. The reason carbon is so versatile, the reason it can create this whole universe of different materials, it all starts right here, with the simple, elegant, yet powerful ways its atoms can connect to each other. It's an amazing reminder that sometimes the biggest differences come from the smallest changes in connection.